Mr. Taru, in this lesson we are going to be doing 4 examples: addition, subtraction, multiplication, and then division of combining square roots and then determining what the domain is of our new function. Now, I'm doing this video in addition to a pre-calculus playlist that I've already created. I'll have a link to that full playlist in the description of this video because my students this year are having a pretty difficult time working with the domain, finding domain of functions, ones that include these square roots and other ones that include rational functions. I'll have a little bit of that in this video, and then I'll make another additional video for an extra supplement. We're going to remember that with domain, you cannot square root a negative number and you cannot divide by 0. Now there's all kinds of functions we'll be dealing with this year. Trig functions, natural exponential functions, logarithmic functions, and they all bring in their little different twists into what you can use as far as their domain goes. But for right now, we're just dealing with division or fractions and square roots. And you cannot square root, or indeed even root, a negative number. And one more time, you cannot divide by 0. So we're going to be dealing with and thinking about these restrictions on the domain as we go through these problems, which is going to start with f of x is equal to the square root of x plus 3, and g of x is equal to the square root of x minus 1. Just using that function notation because we're using 2 different functions at the same time, so we need a name to call them. Now, we're going to add these functions, and we're going to subtract. Okay, that just simply means take function f, which is the square root of x plus 3, add it with the function of g of x, which is the square root of x minus 1. And as far as simplifying goes with this problem, well, there's no simplifying to do. Remember, like if you have the square root of 2 plus the square root of 3, that is not equal to the square root of 5. You cannot add radicals unless the numbers inside the radicand, or the radical, the radical, are the same. Like if I have the square root of 2 plus the square root of 2, maybe we'll make this a little bit different, add another 2 as a coefficient. And if I say we're going to add these radicals, well then all you're going to do is recognize that they both have the same index. They're both, square roots. It's not like a square root and a cube root. And they both have the same number underneath the radical. Well, if that's the case, to add these square roots, we're simply going to add the coefficients out front, and this becomes 3 times the square root of 2. But with, of course, the algebra we're working on with right now, and me writing the square root of x plus 3 plus the square root of x minus 1, well, we don't have the same value or same expression underneath these square root symbols, so we're not going to be able to add those together. And so we kind of can easily set up, therefore, the subtraction of these 2 functions. We have the square root of x plus 3 for the f, which is first, and then minus the square root of x minus 1. So not too much interesting going on with this first problem. And as far as the domain goes, the addition or subtraction, that is not going to make any difference in determining the domain. All we have to remember is you cannot square root a negative number. So for determining domain, all we're going to do is make sure that that doesn't happen. So we're going to see that each of these equations have 2 conditions. We have to make sure that the expressions that are in each one of these radicals remains equal to 0 or is positive. So we're not focusing on what x can be equal to. We're focusing on making sure that these expressions remain greater than or equal to 0. So we have both x plus 3 has to be greater than or equal to 0, as I write 3, and that's a interval notation for and. If it was the other way around, if it kind of looked like a U shape, that would be or. So that's and. X minus 1 also has to be greater than or equal to 0. So it's kind of like we're recalling how to solve compound inequalities, because both of these inequalities are in the same equation. We have x has to be greater than or equal to negative 3 as we subtract 3 from both sides. And as we add 1 to both sides, we get x has to be greater than or equal to 1. Now, as far as, which one of these are the answers? Well, both of these together have to pass because both of these conditions are coming from the same equation, whether it's the plus or the minus. So on a number line, we're going to come through here, and we're going to recognize that when we remember graphing inequalities on a number line, we used a solid dot on that value to represent the equal sign. So we have x is equal to, so a solid dot at -3 equal to or greater than -3. We have this condition here, which is that x has to be greater than or equal to +1. And I need to look at this number line and make sure that I'm choosing the part of the number line that satisfies both of these conditions. Like if I pick a number out here like -4, well, -4 plus 3 and -4 minus 1, both of those expressions are going to come out to be, or both of those, yeah, these expressions are going to give us negative values. And of course, again, unless we're talking about imaginary solutions, you cannot square root a negative number. If I pick a number like -1, you see that it's the only inequality that's over here at -1, it's satisfying the fact that this is going to be positive. -1 plus 3 is 2, which is greater than or equal to 0. And you can see the shading on the number line here. But I don't have the shading for both of these inequalities, say here at -1. If I put -1 minus 1, I get -2, which of course is not greater than or equal to 0. So I'm going to come through here. Neither one of these conditions are satisfied. Here, only this condition is satisfied. Nope. This is the part that we want. This is where we have the shading that is satisfying both of these inequalities. Both of these expressions need to be greater than or equal to 0 so that we can take the square root of those values. So our final answer for the domain is that x needs to be greater than or equal to 1. And that's what the answer looks like with inequality notation. If you want to write it in interval notation, you'll use a square bracket indicating equals to. Starting at 1, always go to the low value first, and then up to infinity and beyond. And that's what your domain looks like in terms of interval notation. So that is the combination of two functions, two square root functions using addition and subtraction, of course. Let's get on to the division. So we're going to do the combining of these two functions with division. We have f over g of x, and that just simply means, take function f, square root of x plus 3, and put it over g, which is the square root of x minus 1. Now, we like to always tell our students that we want to never have a square root in the denominator. We want to rationalize that denominator. Multiply the numerator and denominator in this case by the square root of x minus 1. But you never want to determine domain when you have manipulated or simplified your equation. You want to find your domain as soon as you set up that combination of functions, or we're going to be talking about later in this section for compositions. So I'm going to leave this in this format and understand a couple of things. We have two square roots in our equation again, and with an even root, you cannot even root, one more time, a negative number. So we might think that, like before, well, the expression of x plus 3, which is in the square root in our numerator, has to be greater than or equal to 0, and with interval notation, because in my pre-calc class we use interval notation, the expression of x minus 1 has to also be greater than or equal to 0. So it looks like we're going to be setting up conditions for our domain, just like in the previous screen. And we're going to be talking about trig functions, logarithmic functions, and all different types of functions this year. And we'll have different situations of how we need to restrict the domain of those functions. What numbers can you basically restrict? What numbers can you not put into this so you get an undefined situation? You cannot square root a negative number, but you also cannot divide by 0. So I need to think about this other condition here and remember that, oh, well now this question, unlike before, involves division. So if I have a variable in the denominator, I can't just think about, oh, you can't square root a negative number. I also may have to make sure that that x minus 1, yeah, this is a good condition if it's just something equals the square root of x minus 1. But now that the square root of x minus 1 is in the denominator, and I need to make sure that it also does not equal 0. because you can't divide by 0. And now this is going to look very, very similar to what we just got done doing. The main difference here again, as we look through the number line and look for areas within this number line that satisfy both of these conditions, because they're both coming from the same equation and working together at the same time, is we have an open dot here at 1 because there's no equal sign. And it looks like I'm indicating the same shading as before, just going to the right of 1 as my final answer for the domain, that interval that satisfies both of these conditions, but we're not including 1. So what that looks like with interval notation now is that we're going to start at our minimum value on the number line of 1. We're going to go to infinity again and beyond. Infinity is a theoretical value. We never stop going up, so we can never use a square bracket around infinity. And this time, because there's an open dot at 1, we're not including the value of 1. We're not going to use a square bracket again. We're going to use a set of round parentheses. And if your class is using just inequality notation for the domain, you can of course say that x has to be greater than or equal to 1. And this problem was a challenge for some of my students, remembering to not include the equal part of this inequality from the domain because you can't divide by 0. But we really are working out this lesson for the last example, which involves multiplication of these square root symbols. Alrighty then. We have the product of f and g. Well, that means that we're going to take the square root of x plus 3, multiply it by the square root of x minus 1, and voila. Now, while we talked earlier about not being able to, well, that was the final answer, wasn't it? Yeah. While we talked about earlier, there's a lot of restrictions involving the addition and subtraction of radicals. You need to make sure that you have the same index. These are both square roots, little indexes of 2. We don't need to write. Well, we need to write there. Don't need to write. We have the same number inside the square root symbol. And when we add those radicals, we actually don't add those numerical values underneath the square root symbol. We're actually just adding the coefficients. The 2 plus 1 is equal to 3 square root of 2. But maybe you remember that you were able to multiply and divide square roots. Like, did you remember simplifying things like this? The square root of 32. Could you rewrite that so that there was a smaller number inside the radical symbol? Well, we are taking a square root, so we can simplify this, aka make the number inside smaller by factoring 32 and looking for a factor that, we have that perfect square. Perfect square is like 2 squared is 4, 3 squared is 9, 4 squared is 16. So this 32, the square root of 32, can be rewritten as the square root of 16 times the square root of 2. And then indeed, the square root of 16 is 4 square root of 2. I'm trying to recall some of these older algebra and arithmetic skills that we've used in the past to help you figure out this particular problem. Yes, you can multiply numbers, numerical values or expressions that are inside, like radicals, in this case, square roots. So, and I didn't rationalize the denominator for the previous question simply because I was okay with just the setup of the division and then talking about the domain. So here we have, well, the square roots. We have x times x, which is x squared. X times negative 1 is negative 1x. We have 3 times x, which is positive 3x. And then 3 times negative 1 is negative 3. Excellent. Now, how do we make sure that this expression is going to remain positive? Probably the hardest domain question out of this entire section of my pre-calculus book, or probably your book, whatever you're using at this time. We need to make sure that x squared plus 2x minus 3 remains greater than or equal to 0. So we need to remember how to solve basically quadratic equations, second degree equations. And we can do that by factoring, which should be pretty simple because we actually got this x squared plus 2x minus 3 from the two factors of x plus 3 times x minus 1. And again, that has to be remain become or remain greater than or equal to 0. Now, if we were just solving a quadratic equation by factoring, we would set each of these factors equal to 0. Solve them, so subtract by 3 and add by 1, and you'd be done. You know, because the solution to equations normally only have like one or two, you know, maybe, I mean, they can have more than just one or two solutions or no solutions, but there's usually like a limited number. Whereas with inequalities, there's basically an infinite number of solutions for almost all of these problems. So this is not the solution to this inequality. So there's two ways to do this. You can solve what's basically called solving polynomial inequalities. I have a video for that in my playlist. Again, you'll find that link in the description. And in my pre-calculus book, we haven't even talked about solving rational or polynomial inequalities. So this is what you're going to do. You can look at it two ways. You can put these values on the number line, mark them as sort of like test points, if you will, or important points along that number line, and set up three different intervals. You've got an interval here, 1, an interval here between -3 and 1. What's your second interval? And then you have a third interval from everything to the right of 1. And you can think about putting numerical values within this expression, one from this interval, and this interval, and see if this expression would come out to be positive or negative, like if you go to -4, right? If you go to -4 and you think about putting a -4 into this expression, -4 plus 3 is -1, so that's negative. -4 minus 1 is -5, so that's negative. And so we have a negative number coming out of this factor, a negative number coming out of this factor, and of course it's x plus 3 times x minus 1. And I don't really care what that value is when you plug it in, but I'm just trying to see if it's greater than 0. And of course a negative times negative is positive. Any positive number is greater than 0, so this is an interval which will work. We can put in -1. -1 plus 3 is positive. -1 minus 1 is -2, or just a negative number. And a positive number, thinking about plugging in -1 or -2 or 0, a positive times negative is going to be a negative value, which is not greater than 0. And then finally, we can plug, say, 2 in. 2 plus 3 is 5. 2 minus 1 is 1, both positive. And when you multiply two positive numbers, you get a positive answer. So I can sort of test values along the number line, set up those intervals set up by the solutions to the equation, if you will, setting that equal to 0. And I can say that my final answer, my domain, is that x cannot, well, let's see. I was going to say not equal to, but values from -infinity up to -3 worked, and we can include -3 because this isn't like in the denominator of a fraction, and we can square root 0. So we go from -infinity to -3, use that square bracket because it's okay if this value is equal to 0, and then we're going to pick up, okay, so if we're in this interval, negative times negative is positive, pass. If we're in the middle, no good. If we're over here at 1 or farther to the right, anything 2, 3, 4, decimals of course are okay, positive times positive is positive. And that's how I taught finding or solving polynomial inequalities in my old video. But we're also going to be talking about graphing polynomial functions. And I don't know if this is a review, a preview, or whatever kind of experience you have in your class as you're watching this video lesson, but you can also come up with this solution with just really kind of thinking about, well, what this graph looks like. And let's highlight this in, what color have I not used yet? Green? Okay, here we go, green. Y equals x squared minus 2x minus 3. This is a second degree equation. This is a power of 1. There's one variable, just x, second degree. This is a quadratic equation. This is a parabola, and we have a positive leading coefficient. So if you know a little bit about your polynomial functions and graphing, we have a parabola opening up. And this parabola opening up, if you think about, remember finding x-intercepts? When you found an x-intercept, you let y, oh yeah, equal 0. And you would finish solving that by factoring. So all these skills we're learning are tying together. So this parabola opening up has x-intercepts at -3 and +1. We've already kind of done that work of finding x-intercepts when we were graphing parabolas. So each of these tick marks are 1. So here's an x-intercept of 1. Here is an x-intercept of -3. If you did just cover graphing polynomial functions, you will also hopefully remember this. And if not, I'm going to remind you. This solution of -3 came from this factor that only showed up once. This answer of 1 came from this factor that only showed up once. You remember talking about multiplicity of zeros? If the multiplicity is odd, if the multiplicity is odd, then the graph passes through those x-intercepts. I should have put x-intercepts. I was running out of room. So this parabola looks something like this. Oh, we can talk about letting x be 0, and this is 0, and your y-intercept therefore is -3, and all kinds of stuff. And you might have thought, well, man, that's really complicated. I would have never thought about that. Well, if you haven't talked about graphing polynomials, then yeah, drawing a picture or even visualizing it in your mind to solve this inequality maybe not be might not be your first choice. But if you do know your polynomial functions very well and how they look graphically, recognize that parabola opening up, then you might realize that, oh yeah, this function is only going to give me positive values or values equal to 0 over here, starting at 1 and going to the right. See how the graph's above the x-axis? All those answers, all those y values are positive. So here's your domain, at least in terms of your solution, at least in terms of this inequality. From 1 to the right, your answers are greater than or equal to 0. And from -3 to the left, your y values, your answers, are also, again, greater than or equal to 0. So you can see the domain in this picture, those y values, that graph giving you positive values. Just trying to tie in all these things you're learning through your algebra and now pre-calculus classes. I'm Mr. True. Bam! Go do your homework.